Okay, yeah, so we'll kick off then. So thank you everyone for coming. Thank you so much, Matteo, for joining us and for accepting our invitation. We're really thrilled to have you speak today. So to introduce our speaker today, Matteo Guainazzi is a staff astronomer at the European Space Agency, also known as ESA, and he earned his PhD in astronomy from Università La Sapienza in Rome in 1996, where he analyzed data from the JAXA X-ray satellite ASCA to investigate the astrophysics of the innermost kiloparsec of active galactic nuclei, an area that remains central to his scientific interests. Over the past 2 decades, he has been responsible for several aspects of the science operations of major X-ray observatories, including ESA's XMM Newton and JAXA's Hitomi mission. As an XMM Newton calibration scientist, he serves as the chair of the International Astronomical Consortium for High Energy Calibration from 2007 to 2017. As of 2016, I believe, he's the ESA project scientist for the NewAthena mission, and also prison missions at ESTEC. As a native of Sicily, he is 59 years old. So Matteo, the floor is yours. What we'll do, if you're happy with this, is that you'll give your talk and then we'll take questions.
Yeah,
and just, I have to leave to give a talk, but Tirso will run the Q&A. So the floor is yours. Thank you, Tony. Thank you so much.
Yeah, thank you very much, Julia, for the nice introduction and for inviting me. I would like first to apologize not to be there in person. Unfortunately, this year my travel have to be cut a lot due to personal circumstances, so it was simply not possible for me to come to the US. But I'm still very glad, of course, of the opportunity of talking about NewAthena and the science and the status of the mission, and we are very close to a critical milestone, as I will show in my last slide. But before I enter into the science or the main meat of my talk, allow me a few moments to pay tribute to a very important scientist in the history of NewAthena. Mike Ruiz was emeritus professor at the University of Birmingham and passed away recently in February 2026. Mike was one of the pioneers of gravitational wave astronomy. He played a pivotal role in LISA Pathfinder. But the reason why I'm mentioning at the beginning of my talk is that for 2 years he was the chair of the NewAthena Science Redefinition Team, a board that ESA appointed to redefine the science case of a mission after some crisis related to overcost of a previous mission concept in 2022. And Mike was the person who presented and defended the science case of a mission as a flagship mission in front of a science program committee of ESA that reinstated the mission in the program. And it's thanks to his vision, his leadership, and his hard work if I'm standing here in front of you talking of this exciting undertaking. So why was even a gravitational wave astronomer so excited with NewAthena? So let me make a bold guess. I guess that in 10 years' time, we will be still very interested, will be still striving in understanding the evolution of baryons over cosmological times. Probably by that time, Euclid will have helped us to understand the astrophysical nature and maybe even the physical nature of dark matter. But still, we will be interested in understanding how in the cosmic waves structure shaped by dark matter, baryons evolve. And in our understanding of the universe, there are a few special places that are key laboratories in order for us to understand the cosmological evolution of baryons. Galaxy cluster at the node of these filaments, and AGN, that creating supermassive black holes that are too small, of course, to be visible in this 100 megaparsec square box of the universe, or at least how cosmologists imagine the universe looks like, but are obvious from the explosions that you see actually injecting materials, injecting energy and metals in the surrounding environment. And X-rays play a special role to understand the special regions in the universe. There are several reasons why this is the case. One of them is shown in the plot on the left side, which is a phase diagram of baryons in the universe, in the local universe in particular, which is coming from a particular cosmological simulations, but many cosmological simulations give essentially the same picture, which is telling us that the majority of the baryon in the universe have temperature and density that are inevitably prone to emit copious X-rays. So X-rays are a privileged wavelength in order to probe the bulk of the baryons in the universe, especially those that are locked into the large scale structure shaped by dark matter. And the second reason is shown on the right side. This is the spectral energy distribution of a typical active galactic nucleus, in fact, of a collection of a sample of active galactic nuclei. And in these plots, all the curves in the blue tones are galaxies and all the other colors are AGN. And AGN stand out because if you look at their high energy emission, the contrast against all the other wavelengths is very high. So from this plot, you immediately gather that X-rays are a privileged waveband to look at creating supermassive black holes. But more fundamentally, by looking at X-rays, we look at the innermost region of accreting black holes where matter is probably shaped by general relativity effect. So AGN are also a probe of general relativity in this sense. So what does NewAthena, this future mission of the European Space Agency, offer? I will talk more about the mission profile later, but in order for me to have a smooth narrative during my talk, I would like just to remind you that the NewAthena is being designed on three fundamental pillars, technological and scientific pillars. The first one is the largest space-qualified X-ray mirror for astronomy. And when I say large, in particular, I refer to the fact that we are able to compact a very large effective area and with a good angular resolution in an area, in a mass, which is compatible with this telescope to be flown into space. And this required a new technology, silicon peroxide technology, which has been developed by ESA over the last 2 decades, granting more than 1 square meter of effective area at 1 keV, with an angular resolution in terms of half energy width of the order of 9 arc seconds. The second pillar is a microcalorimeter, an integral field unit spectrometer in X-rays, the XFU, led by CNES and IRAP, that will be able to deliver an energy resolution of better than 4 eV, which means a resolving power larger than 1000 in the hard X-ray band, over more than 1500 pixels, each of them of 5 arc-second size. So this means a diameter, a field of view of the instrument of the order of 4 arc minutes. And last but not least, we plan to have as a third pillar another instrument that will constitute the fastest sky X-ray survey ever flown into space. It's a wide field instrument. It's an instrument led by MPE, an active pixels, active sensor instrument with a standard energy resolution like CCD cameras, but a very large field of view of 40 times 40 arc minutes. And at the core of this mission, as said, we are designing the largest X-ray observatory ever qualified to space with this new technology. It's a modular technology which essentially put together a large number of small modules like the one represented in the picture on the right side of the slide. We are going to assemble 500 of these modules made of stacks of silicon plates on a structure which will be of the order of 2 meters wide, 2 tons of mass. And this kind of mirror will be able to deliver an effective area, will be at 1 keV, 2 order of magnitude larger, at 6 keV, 1 order of magnitude larger, than any existing operational instrument available on the market. This plot of the effective area, this comparison in particular is for the XIFU spectrometer, so the spectrometer on board the NewAthena compared with other existing spectrometer, the XMM-RGS and the Resolve CRISM and the Chandra energy transmission grating. And unfortunately, the comparison with CRISM has to be with the light green curve, which represent the gate valve close configuration. Now, NewAthena is being designed to address a very large set of questions, but there are 6 key questions that are driving the design of the mission that I list here. And I will go through this question in pairs, just because the kind of object that will allow to address these questions are analogous, are similar. So let me start with the first 2 questions, which are how do the largest cosmic structure form and evolve, and how is the universe enriched with metals? And it's very natural to me to start this journey through the new science that Athena is going to deliver by starting from some recent results obtained by CRISM. Now, CRISM, this Japanese-led satellite mission of X-ray of the Japanese Space Agency, carries an instrument, a microcalorimeter, which is conceptually similar as the XIFU, but on a much smaller telescope, so a smaller effective area, and with much larger pixels in the sky of the order of 30 arc-minutes side. This means that the capabilities are not so extraordinary as NewAthena, but still they've represented in many areas of astrophysics a revolution. And here I want to start with one of the most puzzling results obtained by CRISM so far, the measurements of low turbulence velocity in the intercluster medium of clusters in the local universe, even when you see large bulk motions like in the case of a coma cluster. And typically this implies that the non-thermal pressure in the intercluster medium of this object is constrained to be lower than 10%. Now, this is in itself strange because especially in object or in region of clusters where you see strong feedback in the intercluster medium from an AGN, from a relativistic jet, you may expect a very high turbulent velocity or much higher turbulent velocities. And maybe this is partly the case intrinsically, but there are dilution effect due to a poor CRISM spatial resolution. But if you look at these results at face value, these results are inconsistent with all cosmological simulations. And therefore, there is some microphysics that we do not understand, fundamental microphysics that we do not understand in the interaction between supermassive black holes, jets emitted by supermassive black holes, and the hot gas in galaxy clusters. And just to remind you, the simulation I showed at the beginning, these are the loci where you saw the big explosion at some specific area at the nodes of the cosmic web. Now, with Athena, we plan to make a fundamental step forward on that and probably to understand what's happening, because something that CRISM cannot do due to its limited spatial resolution is actually to tell us what is the microphysics of the interaction between the AGN and the intercluster medium. In order to do that, we need to be able to perform spectroscopy in X-rays on spatial scales that are sufficiently small that match the area in the sky where we actually see this feedback, this interaction to happen. Cavities, bubbles, they have been imaged, but very deep observation with Chandra of nearby galaxy cluster. You see an example of these images in the right side of the plot on the right side of the slide. The images are Chandra images. And what I compare in these images are the field of view of the XIFU. So you can see that the XIFU has a field of view that is perfectly matching the size of the galaxy cluster in the nearby universe. And the green square represents 4 XIFU pixels, just to let you know that we actually, with XIFU, and thanks to the angular resolution of the optics, we will be able to perform a spectroscopy of each of these regions where we see depression and enhancement of X-ray surface brightness profile that are indicative of insight of interaction between the AGN and the cluster. Another thing that CRISM will have a very hard time to do, but will be easy for Athena, is extend the measurements of this turbulent velocity to regions beyond the innermost core of the clusters. So beyond what the experts call R500, virial radius of a cluster, so the radius where the density of the cluster is corresponding to 500 times the average density of the universe. And this will allow us to study actually two different regimes, going from the regime where we expect the kinematics of the cluster to be dominated by a GN feedback to a regime where we expect actually the cluster to be instead dominated, the kinematics to be dominated by secular cosmological process, by merging, for instance. Another thing that you in this moment is beyond the CRISM capabilities and will require much better effective area and the spatial resolution is making an important step forward in the study of the baryon cycle of the universe. So we suspect that there is a sort of feedback mechanism or a sort of outflow-inflow mechanism that essentially on one side drives matter outside the galaxies due to stellar winds, AGN jets, or supernova explosion. But then eventually this matter, they condensate in hot halos surrounding the galaxy. They have to come back to the galaxy in order to feed the star formation cycle. And this kind of cycle is something that cosmological simulation predict. And now cosmological simulation make, since a couple of years, very specific prediction of what would be the imaging and spectroscopic properties of the X-ray emission associated to very hot gas in these halos, in the so-called circumgalactic medium surrounding the galaxies. Now, NewAthena will be able to achieve a breakthrough in this area in two ways. On one side, on the imaging, using the deep imaging capabilities of the WFI instrument by looking directly at the halos, the analogous, if you like, of the Rosetta Fermi bubbles in our galaxy, that will be possible to be imaged by WFI in even relatively short exposure of the order of 1 day. In the left side plot, I show a comparison between the expected soft X-ray emission of AGN-driven bubbles in Milky Way galaxies as expected by cosmological simulations on the upper side. And the lower side, you will see the corresponding WFI images showing that if actually this halo exists, this bubble exists, we will be able to detect plenty of them with WFI in relatively short images. But there is another avenue to characterize the CGM, the spectroscopic properties of a halo, is by looking at spectroscopy, because we will, the resolving power of XIFU will be so good and so good in the energy range, which is most critical in this case, where you see transition of helium-like and Lyman alpha's oxygen, that by looking at system with sufficient redshift larger than 0.035, we will be able to separate the emission due to the halo of this galaxy from the overwhelming emission due to our own galaxy, which are the very strong emission line that you see in the simulated XIFU spectrum on the right side. So to be clear, the emission of the hot halo of this galaxy at 0.035 redshift are actually the tiny enhancement that I point now with my mouse, not the big lines due to our galaxy, but these tiny lines will be sufficiently strong, sufficiently separate in energy due to the cosmological redshift of the system that we will be able to characterize them and therefore provide physical measurements, density and temperature of the CGM. Another area on which Hitomi and CRISM have made an important, very important contribution is the measure of the metallicity of the intercluster medium in nearby galaxy cluster. This is already a result that had been obtained by Hitomi 10 years ago. The rather surprising discovery that the metallicity of the intercluster plasma in the Perseus cluster was very similar to the solar abundances. These are the black point in the plot on the left side where the metallicity is shown as a function of the atomic number. Now, this might be a coincidence or not. There might be some physical reasons for that I don't have time to delve into it. But the important point of these results is that the metallicity of the intercluster medium is a sort of fossil outcome of the integrated explosion of million and million of supernova remnants over cosmological times. So essentially, by looking at the metallicity pattern of the ICM in the local universe, we can actually reconstruct what is the fraction of supernova remnant and what type of supernova remnant were responsible for the metal abundance pattern that we observe in the universe. So this was done by CRISM and was done by Tommy, is being done by CRISM. So this is not an area where NewAthena will produce a significant breakthrough and advancement. But something that NewAthena will be able to do, thanks to the better effective area, is extending these measurements to high redshift. So to the systems at galaxy clusters at an epoch where these clusters started to form. So we will have the opportunity for the first time to study the evolution of the metallicity pattern in the universe and therefore indirectly make a cosmological history of nucleosynthesis. What I show here on the left side is a simulated spectrum of a fiducial cluster at redshift 2 with a temperature of 4 keV. All the emission lines are, of course, shifted due to the cosmological redshift. And you see that we can, with a relatively deep but not extreme, not dramatically sleep, a few days of observation with XIFU, we will be able to measure emission lines from manganese to iron and possibly even nickel, and measure metallicity with statistical and systematic errors lower than 20% for manganese. So we will have the possibility of measuring metallicity on high redshift cluster, on a large number of high redshift clusters. And this will allow to extend us the constraint on the nucleosynthesis that we are obtaining now with CRISM in the local universe to redshift 1 or even 2. This is an example from simulations done by François Mernier on XIFU observations of typical cluster at redshift 1. And there is the interesting possibility that this measurement will even allow independent constraint on the initial mass function. I jump now to the second pair of questions, which has more to do with compact objects accreting neutron star, black holes over the whole stellar mass, and the fundamental question of how do black holes grow and they impact the cosmological evolution of their host galaxy. Let me start with a bit of an old plot that is 2 years old. It's curious to see that plots that are 2 years old are now already old in a sense, because this represents the expected log n log s of active galactic nuclei that we expected 2 years ago to measure with the WFI in a typical survey strategy that, of course, it's very similar to the survey strategy we think about it today. So these are in 3 different redshift range, the magenta points compared with other kind of determinations. And the point that we were making at the time this plot was made, the reformulation, that most likely these estimates were very conservative because the initial results by JWST, which are indicated in the green dots in the green areas and this blue single detection at that time of an AGN at redshift around 10, they were suggesting a much larger, actually, by order of magnitude, much larger density of AGN at high redshift. And therefore, our predictions were, we said, very conservative. And therefore, there is an enormous discovery space available for NewAthena. Now, by now, of course, we have many more measurements and many more larger sample of the high redshift AGN. And recently, a paper has been published suggesting that maybe the original estimate of the luminosity was too optimistic, but still there remains an enormous discovery space available for NewAthena in order to pinpoint many of these objects at redshift larger than 5. Now, there is, of course, a potential issue that is well aware to all of us who are looking at actually this issue is mostly all of these very high redshift AGN detected by JWST they seem to be extremely X-ray weak, at least apparently X-ray weak. If you look at most of these little red dots individually, they actually, you detect only the upper limits, and in some cases, so constraining that they are inconsistent with the relation between X-ray luminosity and H-alpha luminosity that you observe in the local universe. Now, why are they X-ray weak? Well, they might be intrinsically X-ray weak. In this case, there is probably little that NewAthena can do, but they could be actually weak, only apparently weak, because they are strongly absorbed, strongly obscured. And there is a recent paper from which I extracted the plot on the right side that stacking together Chandrase's images of redshift larger than 2 AGN measured by JWST got actually a detection in the rest frame energy larger than 10 keV. If this is true, it is a general rule for the highest redshift JWST AGN. Athena will, of course, have the perfect sensitivity, the perfect effective area in order to detect actually this highly obscured AGN. And that will be actually the only way in order to detect this AGN observation. But once we are not, of course, it's very interesting to look at what this new mission will be able to do on the AGN, the early universe, because of course we are all intrigued by understanding how it is possible that 10 to the 8, 10 to the 9 solar masses can actually be gathered, accumulated in just a fraction, 5-10% of the history of the universe. But the WFI observation will allow us to create a catalog of hundreds of thousands of AGN, most of them actually at much lower redshift. And one of the basic questions that we expect we will be able to address with this larger sample of AGN is understanding the mechanism of AGN feedback, so the mechanism through which possibly supermassive black holes are able to regulate star formation in their own galaxy. Now, the hypothesis, of course, that it's underlying my statement is that feedback exists and is regulated by powerful winds that are ejected close to the black hole. And this wind can do either of the two things to the interstellar medium, either hit the interstellar medium up to a temperature where gravitational collapse of molecular clouds become impossible, and therefore you don't form star any longer once the black hole reaches a certain mass that is proportional to the energy of the outflows injected in the ISM, or the momentum that these outflows give to the interstellar medium is so large that simply the galaxy is deprived of matter. There is no longer gas available to do any stars. Now, feedback is, of course, a very nice and buzzword in the recent observational cosmology. In itself, it would deserve many talks. Let me just mention one of the key results or the contribution that X-ray spectroscopy has provided recently to this field by demonstrating for the first time in an unambiguous way that supermassive black holes launched at subrelativistic velocities close to a black hole, they do exist, and they are actually clumpy and probably ejected very close, 100 of gravitational radii from the black hole event horizon. And by making this very accurate spectral interpretation and decomposition of the absorption line due to these relativistic outflows, it has been possible for the first time to measure in a very robust way the energy and mass output of this outflow. And not surprisingly, this estimate of the output is not surprising. Well, surprisingly, of course, but in a sense, we could have expected the previous measurements were wrong by a large factor. These estimates of the energy and mass outflow rate are between 60 and 300 times larger than estimated with instruments like CCD instrument, which much poorer energy resolution in the past in X-rays. So this means that for the first time, we have a clear smoking gun in terms of AGN feedbacks, in terms of these relativistic outflows emitted at 20-30% of the speed of light, very close to the event horizon. Now, with the WFI survey, we will detect probably of the order of 400,000 AGN at any redshift during the 5-year nominal mission. And these will enable us to find many AGN with strong relativistic outflows, what in jargon are called ultra-fast outflows, a speed of 20-30% of the speed of light, at the cosmic noon, which is where actually we want this object, we want to find this object, because the cosmic noon is exactly the moment in the history of the universe where the density of accreting black hole and the density of star formation peak. So it's the moment in the history of the universe where we want actually to see whether AGN feedback is in action and what it does to the history of star formation. But in order for us to be able to understand actually the physics of this outflow, and this is required in order for us to make reliable estimates of the outflow rates, mass outflow rate, and energy, kinetic energy outflow rate, we need to be able to pinpoint what the acceleration mechanism of these outflows is. And the acceleration mechanism is very elusive, it's very difficult to find the ultimate smoking gun of whether the winds are emitted by the radiation pressure of the AGN or by magnetic fields or they are simple thermal winds due to the fact that at some point the gas is heated to temperatures whose velocity, escape velocity is larger than the escape velocity, local escape velocity. But the key mechanism in order to pinpoint the launching and acceleration mechanism is studying the profile of absorption line in X-rays, because the winds driven by magnetic fields and winds driven by radiation pressure would have completely different, it's expected with completely different profiles of their absorption lines. So only with Athena we will be able actually to be made these measurements in order to pinpoint the acceleration and launching mechanism. And this applies to creating supermassive black holes, but of course this applies also to compact objects, stellar mass black holes and neutron stars, where these ejection phenomena occur. As a byproduct, it's funny to say, but as a byproduct of all of these spectroscopic activities, we will be able, with NewAthena, with the XFU measurements of NewAthena, to provide the first reliable distribution of black hole spin in the local universe. And this distribution is a fossil remnant of a history of merging the accretion of the host galaxy. If the host galaxy go through a sequence of mergers followed by chaotic accretion, we expect the distribution of black hole spin in the local universe to be skewed towards Schwarzschild, toward black spin 0. If we have only mergers, there is a sort of magic value of 0.69 of the spin where the distribution will be peaked, but the distribution is expected to be rather flat. If we have instead a prolonged episode of coherent accretion, we expect the distribution of spin in the local universe to be skewed toward maximally spinning. And with just 1 day of observation of XFU, we will be able, in a standard kind of AGN in the local universe, we will be able to constrain the measurements of the black hole spin with very high accuracy, as shown in this contour plot of the black hole spin of the x-axis versus another parameter, the density of a worm absorber on the y-axis, for 3 different values of the spin. And this, I would like to stress that this simulation takes into account all sources of systematic errors, including our understanding of systematic errors on the underlying model of accretion disk. But maybe even for some of us, even more exciting, the possibility of actually delving into astrophysics of very dense matter by nailing the equation of state of neutron star. The equation of state of neutron star is observationally constrained by 2 quantities. One is the mass of a neutron star, and the other one is the radius of a neutron star. The former quantity is relatively easy to measure. The latter quantity is less easy to measure. But recently, NICER have made an enormous advancement in this field by making observation and which allowed to model the energy-dependent pulse profile of rotating pulsars and getting unprecedented constraint on the radius of a couple of neutron stars of the order of 15%. Now, 15% is an astonishing achievement for NICER, but is still insufficient, as shown in this plot, to constrain significantly the innumerable families of equation of states that are currently on the market. If we want actually to make a step forward, we need statistical errors of the order of a few percent, and this is what NewAthena will be able to deliver. Let me go quickly to the last two questions that are more related to stellar phenomena. One of them is, of course, a sort of mandatory science case for any future mission, which is how NewAthena will be able to contribute to multi-messenger astrophysics. NewAthena will be able to observe a few tenths of electromagnetic counterparts of neutron star merging events, up to an horizon of the order of redshift 1. And in the plot, this is compared with the expected distribution of neutron star merging, and black hole merging, as it will be observed by the future generation of gravitational wave ground-based array. This is enabled by the fact that the mission, even if it's not designed to follow up transient events, will have still a large field of regard and a relatively fast TO response time. Relatively fast, of course, for missions that are observatory class. They are not like SWIFT that was, of course, designed in order to achieve astonishingly rapid response time. Now, the key contribution of NewAthena in this field will be the accurate determination of jet inclination for most of these binary systems. And this will allow new science in three areas. One is cosmology, because the measurement of inclination allows to resolve the degeneracy that prevents the determination of the luminosity distance. The second is the nature of the remnant of the merging. What kind of compact object will remain through the study of X-ray variability that NewAthena will be able to do at astonishing accuracy. Whether it will be a compact, a black hole, or a neutron star can be actually ascertained by looking at the nature of by looking at X-ray variability. And last but not least, it will improve the metallicity determination in kilonovae by disentangling the contribution of non-thermal emission. Now, NewAthena will be an X-ray observatory. So at that point in my talks, I always say all the science case I've presenting to you so far is not really relevant, because what NewAthena is going to observe will be decided by the science community by the time the mission flies. And you know, NewAthena, the science case of NewAthena actually encompasses many more aspects than I had time to describe and to present in my talk. I've given you just three other examples of what XIFU will be able, for instance, in terms of determination of metallicity of rare elements in supernova remnants, pinpointing metallicity of rare elements at the level of 10% of accuracy on the sizes, region of a size of the order of 10 arcseconds. Probing the warm hot intergalactic medium in absorption. I mentioned what we're going to do in a mission, but of course, there will be the possibility of measuring several tens of sidelines using bright AGN or gamma ray burst as a source of backlight. And also stars, and in particular, it's very interesting the possibility of studying stellar flares on very short time scale, on the dynamical time scale of their evolution, which may have actually an impact on the effect the stellar flares have on the habitability of the surrounding planets. Now, why is NewAthena capable of delivering this large range of science? I think this is because it exceeds the performance of any existing X-ray observatory flown so far in three key areas. First of all is the survey speed. WFI will be able to observe, to detect a number of sources in each observation, a rate of source detection, if you like, which is one order of magnitude larger than XMM or Chandra. So this means that we will be able in a single point to accumulate 10 times more sources than a similar pointing of XMM or Chandra enabling you to do. And these up to a flux limit, which is well matching the flux limit of 10 to the 44 AGN at redshift 7 before confusion limit enters into play. And this will allow us to extend, as shown on the right side plot of this slide, which is the flux versus survey area comparing, NewAthena with other existing surveys. This will allow us to go exactly in the regime of measuring and characterizing AGN up to redshift probably 8 that we require in order to give a more complete census of the AGN population down to the epoch of reionization. A second key performance indicator is a spectroscopy, and here I show here a comparison of spectroscopic figure of merit for point-like sources between the XIFU on NewAthena and the resolve of CRISM. These figure of merits are a combination of fundamental instrument properties that tell you how better a given instrument perform in terms of detection of weak lines, measuring the shift centroid of strong lines, and the broadening of strong lines between two instruments. And here I use, of course, the obvious pair, which is XIFU and resolve. If you would put Chandra ETG or XM Newton RGS on these plots, they would be completely invisible. And this means that in the common energy band, the XIFU resolve, the XIFU figure of merit are better than a factor of 30 to 80 than the corresponding figure of merit of resolve. And of course, in the soft X-ray band, unfortunately, I say unfortunately, because everybody would like to see the gate valve close issue in CRISM resolved, no pun intended, but the figure of merit of XIFU exceed those of resolve by an infinite factor. But XIFU is not only going to deliver extraordinary results on point-like sources, it will be a true integral field unit instrument. So this means that we will be able to deliver spatially resolved spectroscopy on a scale that it is completely unprecedented so far, and is a 2 orders of magnitude better than it is possible with CRISM. And this is shown very nicely by this plot that I extracted from a paper recently by Godinot et al., the French group, and they show visually actually by comparing the image of the Tycho supernova remnant in resolve and XIFU. And the green box once again represents the area from which the spectra are extracted. The difference in spatially resolved spectroscopy that XIFU will enable in comparison with resolve, we will be able to perform, as I said, spatially resolved spectroscopy on an area which is almost 2 orders of magnitude smaller than resolve. And this, of course, for complex system like supernova remnant. In this case, I'm showing in particular the Sandra image of a Tycho supernova remnant that show all the complex interplay of ejecta plus shocks in the interstellar medium. This is key in order to understand the microphysics of this system. So let me close with a summary of the mission status. So we are still in a study phase. It has been a long study phase for NewAthena, but we are already preparing actively for what we call adoption. Adoption in the ESA jargon is the moment where the mission is ultimately included in the science program of the agency. And there we start at that point the implementation, which means the industrial contract to build the spacecraft and the instrument for as far as the member states are concerned. As typical for all agency, we have a review that will lead to adoption, which is called, with no big fantasy, mission adoption review, that will start just in a few months. And in order to prepare this review, there are 2 main science activities. One is the preparation of a definition study report, which is a single document describing the mission in a holistic way, but of course with a focus on science that will be delivered in a few months' time from now, and by February next year. But we have decided as a science community of Athena to accompany the preparation of this document that is relatively compact by a special issue that will be published on the Journal of High Energy Astrophysics, to be published concurrently to adoption, and will include 79 papers on astrophysical topics and 16 papers on mission data analysis and modeling. So once the mission is adopted, 6 months to prepare the contract for the industrial prime to start the implementation. And then we estimate we will need an implementation phase no shorter of 9 years that will lead to a launch date around 2037 at least. So with that, I would like to close my talk, and I would like to thank you for your attention. And of course, I would be glad to take any questions you may have.
Is there any questions in the room?
Or online as well, if someone has questions online. Okay, I can ask first. Well, first, Matteo, thank you so much for the talk, and apologies for the technological issues. I would like to ask about the CRISM measurements of low turbulent velocities or velocity dispersion. Because like it's been compared with simulations, right? And simulations show larger turbulent velocities. So how do you think NewAthena is gonna help there? Because I guess like if you have very special resolution, it will still be lower than simulations, right? So how do you think NewAthena will help on that?
I think there are two ways Athena can help. One is, as you alluded to, the spatial resolution. Now, it's true that the spatial resolution may not match the cosmological simulation, but the spatial resolution matches very well the typical size where we see in images of Chandra that something happens, this cavities that are probably excavated by interaction of the supermassive black holes with the intercluster medium, areas where you see evidence for shocks, and therefore they may have other size, interesting size, where you can understand the microphysics of the interaction between the AGN and the intercluster medium. In each of these individual areas, we will be able to derive spectra of this kind of quality, and therefore determine with extreme accuracy velocities, turbulence velocities, densities, temperatures. So I think this will be a tremendous help to understand what kind of macrophysics is happening, and this in turn will help cosmological simulations to actually use the correct receipts in order to describe the feedback. And the second way it will improve is well, in fact, I have answered in two ways, because one way is through deconvolving, disentangling a spatial effect, and the other way is to provide a better physical understanding, which can be used as an input for simulation. So sorry, I thought to say the two things separately, but in reality, in my answer, I merged the two aspects.
Okay, thanks. Yeah, there's one question online. You can unmute yourself and ask.
Hi, Matteo. This is Aneta.
Hi, Aneta.
Thank you. Yeah, thank you for very nice talk and this presentation. I mean, it's exciting to see the mission, being worked on, and some ideas for the future of X-ray astronomy, which we can hope for. I have a question about point spread function shape. If you have any idea of the shape which we could use for the convolution in our methodology development. So that's one question. And the other one is related to pileup. You have very fast readout, but do you expect any pileup in your mission?
Thank you, Aneta. Very good questions. First one is, yes, we know, at least we have a prediction of what the shape of the point spread function will be. As a matter of fact, in our ESA NewAthena Cosmos webpage, we have simulations of the expected images of a point spread function of the Michaux on axis, and we will have very soon also off axis an update from images that we had in the past. And they are based on, it's called modified pseudo